Right, so we are back working on stats again, and this is in Chapter 8. Again, we're working out of the Introductory Statistics from Mann. This is the 8th edition, and we're in Chapter 8. We are talking about confidence intervals. We've previously talked about confidence intervals using X bar to estimate a population mean, that is, using a sample mean to estimate a population mean, and then constructing a confidence interval around that. Here, though, we're going to do something a little bit different. Here we are talking about proportions. We're going to use a sample proportion to estimate a population proportion. Now, let's see what we have here. It says, salaried workers at a large corporation received 2 weeks paid vacation per year. 16 randomly selected workers from this corporation were asked whether or not they would be willing to take a 3% reduction in their annual salaries in return for 2 additional weeks of paid vacation. The following are the responses of these workers. Okay, so we have 16 responses there, just yeses and nos. Okay, construct a 97% confidence interval for the percentage of all salary workers at this corporation who would accept a 3% pay cut in return for 2 additional weeks of paid vacation. Okay? So we're talking here about the people who are willing to take a pay cut for paid vacation. So here we are concerned with the yes responses. Okay, so let's see here. So let's tally up these. It says we have, let's see here, 1, 2, 3, 4, 5 yeses. Okay, so let's go over here and let's write that. Okay, there are 5 yes votes out of 16. My handwriting is still not used to this, but we'll just have to make do. So 5 yes votes out of 16. Now, what does that tell us? That tells us that the sample proportion, or the percentage of yes votes in our sample, is 5 over 16. So that tells us, let's go back over here, that P hat equals 5 over 16. Okay? Oh, let's key that in our calculator. What does that equal in decimal form? 3125. So that is 0.3125. That is our sample proportion. That is, out of our sample of 16 votes, 5 people said that they would be willing to take a 3% reduction in pay in order to get 2 extra weeks of vacation. Now, when we're talking about proportions, in the exact same way we talked about means, we're going to use the sample proportion here, like we used a sample mean, to estimate, except now we're going to estimate a population proportion. So we're going to use P hat to estimate a population proportion. Now, let's get into how we're actually going to do that. Now, just like with confidence intervals for means, we're going to do a very similar process for confidence intervals of proportions. And we have the following formula. Or not formula. Oh, and that is not right. Let me erase that. We have the following expression. P hat plus or minus Z. Oh, I'm not writing very good today. Plus or minus Z times our standard deviation, which in this case is sigma sub p hat. That's how we're going to find our endpoints of the confidence interval. Now remember what this equaled. Z times the standard deviation of our proportion sampling distribution. Just like before, when we were dealing means, it was Z times the standard error. Here we have Z times the standard deviation of the sampling distribution. That is equal to E, which is the margin of error. Okay? So, very similar to what we did before. Now, and again, similar to what we did before, was Z was found by considering the level of confidence we had chosen or were given in the text. Okay, so the text says we have a 97% confidence level. So we need to figure out what Z value corresponds to a 97% confidence level. Now, 97 is one of the pretty common ones, so you may have it memorized by now from when we were talking about confidence intervals for means. If you remember correctly, it's 2.17 is the Z value we're looking for. Now, if you didn't remember that, let's show you how to create that on the fly. Okay? If you didn't remember the Z value that corresponds to a 97% confidence interval, let's just go off to the side here and draw a picture. Okay, that's not the prettiest normal distribution ever, but it gets the job done. So we want to estimate using p hat, and we want 97% of the area under the curve to be centered on p hat. Oh, let's get that a little better there. That's a little messy. So p hat, that's much better. Okay, we want 97% or 0.97 of the area under the curve to be centered around P. Now, what is not shaded? If 0.97 is shaded, and there is 1 is the total area under the curve, what's left over? Well, there is 1 minus 0.97 area that's not shaded. Okay, what does that equal? Well, that's 0.03. Okay, that's in both tails. So right there and right there, left and right, is 0.03. Now, if you want to figure out what is in one of those tails, you just divide by 2 because the normal distribution is symmetric. So 0.03 divided by 2 equals 0.015. Oh, let me fix that. 0.01. Oh, sorry about that. 0.15 in each tail. So right there is 0.015. Right there is 0.015. So what we want is to find this Z, and find this z. And how you do that is using the techniques from when we first talked about z values, and that was in chapter 6 of our intro stats book. Okay. Now, if you go and look up z such that the area to the left of z, like we're talking about this one right here, is 0.015, you're going to get that z equals negative 2.17. If you go and look up in the back of the book to figure out what the area of the curve is to the left of this z value, excuse me, if you know the area of the curve to the left of this z value, which is 0.985, if you look that up to find the corresponding z, you're going to get positive 2.17. Now, as far as the z value goes that corresponds to a 97% confidence level, we pick the positive one. We picked the positive one because otherwise your margin of error would look negative, and margin of error is a distance, and so we want the positive one. Okay, so going back over here, a 97% confidence level corresponds to z equals 2.17. Okay? Alright, so we have p hat, that was easy. That was just the sample proportion. We know that already. We have z, that corresponds to a 97% confidence level. Now what we need to do is find sigma sub p hat, the standard deviation of our proportion sampling distribution. Now, if you remember back from previous lessons, we have that, let's go over here, sigma sub p hat, that is equal to the square root, a big square root, of p hat times, oh, that's a p, not a q. Erase that. Times q hat all over n. Okay, so in this instance, it equals the square root of 0.3125 times, now if p is 0.3125, that is p hat, sorry, we need to find q hat. Q hat, that's 1 minus p hat, which is 1 minus 0.3125. Which, what does that equal? 1 minus 0.3125, and I get 0.6875. So 0.6875. Okay? So 0.6875. Okay? Sorry, getting a little crammed over here. Divided by n. If you go back up here, let's see. 16. N equals 16. That's our sample size. So 16. Okay? So break out your calculator and let's figure out what sigma sub p hat equals. Okay? So we have the square root of, let's see, 0.3125 times 0.6875, and we're going to divide by 16, all under the square root. And it looks like, let's see here, it is 0.1 1,1,5,8,7,8,0,1. Let's go that far. I think that should be good enough. Hopefully, at least. Alright, so that's our standard deviation of the proportion sampling distribution. So, it looks like we have everything we need now. We can actually find our two endpoints of our confidence interval, our 97% confidence interval. So we can write p hat, so we're going here, and we're going to say 0.3125 plus or minus, okay, z we found was 2.17 times our standard deviation. In this case, we found was 0.1158781. Okay? That is going to give us the endpoints of our sampling, of our confidence interval. So remember here, this is actually two solutions embedded in one expression here. Kind of like you had when everybody's done the quadratic formula. You have a plus or minus there in the middle. So one endpoint is going to be found by taking p hat here and adding e, the margin of error. The other endpoint is going to be found by taking p hat and subtracting the margin of error here. Okay, so let's figure out what this is. So this is going to be two answers here. Let's see what those two answers are. Okay, so I'm going to grab my calculator real fast, and we have 0.3125 plus 2.17 times 0.115871. Okay, and that is the upper endpoint, and I get 0.56. I'm going to round to 3 decimal places here. 564. Okay, that's my upper endpoint, and then for the lower endpoint, I'm going to take 0.3125 and subtract 2.17 times 0.115871. Okay, and for the lower endpoint, I get 0.061. Again, round to 3 decimal places. Okay, so there are my two endpoints. If I want to write that in interval notation, so I want to condense this to one solution, or to one, expression, I guess you could say. We have 0.061, comma 0.564. Okay, so there is my confidence interval around my estimate of a population proportion. So again, let's review what this means. So we took our sample proportion, p hat, up here. We added and subtracted a margin of error that was found by multiplying the standard deviation of the proportion sampling distribution times the appropriate z-value, that 97% confidence level z-value. We added and subtracted the margin of error. Okay, and so what this says is, since our level of confidence is 97%, we are 97% confident that our population proportion lies somewhere between 0.061 and 0.564. Now, proportions are percentages, so it's sometimes better to think about these as actually percentages. So we could write, the same information as not as 0. In a percentage form, this 0.061, that is 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1%. 6.1 and then 0.564 is 56.4%. Now, what I'm thinking right here is that's not very useful. What was the entire context here? The entire context was we were trying to take a sample of 16 folks, figure out what percentage of that sample was willing to give up 3% of their salary to get 2 weeks extra vacation a year. 5 out of 16, 31.25%, were willing to do that. Okay. And we used that sample proportion to estimate with 97% confidence the amount of folks in the population who would also share that same sentiment. But look at this. It ranges from 6.1% to 56.4%. That's a very wide interval. Let's actually calculate what E is. Remember, E is the margin of error. So let's do that back in yellow. This right here, that's E. So let's go down here and calculate E, what exactly E was. Because the margin of error is pretty big. I want to figure out exactly what it is. 2.17 times 0.1158781. Margin of error is 0. Oh, I didn't mean to hit that button. Let's see here. Let's erase. Erase. Okay. The margin of error is 0.25. I'm going to round to 3 decimal places again. 251, which is 25.1%. That's crazy. There's a margin of error of 25.1%. Now, just to be clear, this right here is the solution. Okay? Let me just box it so we don't get lost here. So I'm going to answer another question too. That right there is the solution to the problem 8.113 that we are working. Now, if you're working in Wiley Plus, be careful. They may ask you to write this answer, like not in percent form, or this answer. Yeah, they're conveying the same information, but you know when you're working homework online, you have to be careful with how you're requested to enter your information, because if you don't enter it the way you're requested to, you'll oftentimes, or all the time, be counted off. Okay. So, one of those two there is your answer, depending on how you're asked to put your answer in Wiley Plus. Now, I think that's a huge margin of error, and I want to answer, or I want to pose and then answer another question. Let's say that I'm the one doing this research, and I thought I could get away with taking a sample of 16 folks because I want extra vacation and I'm one of the yes votes. Let's say that I'm one of the yes votes and I would gladly take a 3% pay cut to get 2 weeks extra vacation. Again, I'm making this up. I like working, so I'd probably be a no vote in general. But let's just say I was a yes vote. And then I'm trying to convince my boss that a lot of people agree with me. Okay? Well, when you take it to your boss and say that according to what you learned in stats class, that 6.1% to 56.4% of the people at work agree with you, that is 6.1% to 56.4% of the population agree with you, your boss is going to laugh you out of the room. Because he's going to say, that doesn't tell you anything. 56.4 to 6.1%, anywhere in between, that's the kind of people that's the amount of people, the percent of people that agree with you. That's just too big of a margin of error there. What if it's 6.1? Well, that means nobody agrees with you. Well, what if it's 56.4? That means that, well, more than half of everybody agrees with you. That's just way too big. So I go back to the drawing board and I say, okay, I want a much, much lower margin of error. Let's say I am willing to tolerate a 5% margin of error. Instead of a 25% here, let's say I want a 5% margin of error. Okay? Now, the question is, how many people do I need to talk to about my plan to get a pay cut but get more vacation? How many more people do I need to talk to in order to ensure that I have a smaller margin of error? Because if you remember from our last examples we worked in class, the way to decrease the margin of error is to increase sample size. Okay, now we have a formula for that. This formula is going to be a little bit different, than the one we worked with. When we were talking about means, because we're now talking about proportions, but we can do this, the same concept here. If we have a predetermined level of confidence, like for this question I'm answering now, I'm going to leave the level of confidence at 97%. Okay, the sample proportion, p hat, and then of course q hat, those are going to remain the same. But what I want to do is reduce my margin of error, and let's just say 5% is where I want to go with it. So let me change colors down here, get us some more board space. Oh, well, without drawing, so now I'll have to erase that. Okay, so I'm going to do this in green. Again, we've already answered our question, but let's say E margin of error equals 25.1% is way too large. Okay, and we want to figure out what sample size is required to bring E down to 5%. Okay? 5% seems respectable to me. If you go to your boss and say, oh, somewhere between 50 and 60 people, or excuse me, 50 and 60% of employees at this company agree with me that we should take a 3% pay cut but get 2 weeks of vacation, then that might hold a little more water. Now, whether or not it gets passed or not, who knows? But at least the argument holds more water at that point. So now the question is, what sample size is required? Well, we can solve the following equation to figure out what n should be. We have n equals, okay, now this is similar to the last equation we used to find sample size, but it is z squared times p hat times q hat all over e squared. Oh, sorry about that phone ringing. I'll have to let that ring, and I'll have to pick that up in a few minutes. Okay, so that's just going to be, I'll have to call them back in a few minutes, and we will just, we'll proceed. So sorry about the noise. Okay, alright, so there's our formula. Okay, so we have z, that's going to be the same. That's the 2.17 that corresponded to a confidence level of 97%. And then we had, let's see here, z equals 2.17, that's the same. Q hat and p hat, well, p hat, that was the 5 over 16. What was 5 over 16 again? 5 over 16 in decimal form is 0.3125. 0.3125, which then, just like before, that said Q hat was 0.6875. Okay? So, now we can, last thing, E. I said in the in this green text in my new posed problem that I want to bring E down to 5%. Well, what's 5% in decimal form? 0.05. So going over here, we can say N equals. Okay, so we have 2.17 squared times P, which is 0.3125, times Q hat, which is 0.6875. All of that over E squared, which is 0.05 squared. Okay? So let's figure out what N equals here. Okay, so I'm going to use my calculator here. 2.17 squared times P hat, which is 0.3125, times Q hat, which is 0.6875. Take that number and divide by 0.05 squared. And N here, we find out, is, well, approximately equal to 404.671. Now, we did this before. This right here, that 404 represents the number of people, sample size. Now, you can't have, if you're going out and talking to people, you can't actually talk to 404.671 people. Since you need another fraction of a person above 404, we have to say that we need a sample size of 405. Okay? We have to round up to the next whole person because we can't, have a fraction of a person in our sample size. Okay? So, a sample size of 405, this guarantees that my margin of error will be limited to 5%. Now, we could verify that if you wanted to by going back up there. Let's say we could go back up and say, okay, our let's just do that over here. We can say that, just to check, we can say that our sample proportion, our estimate of the population proportion, that was P hat, which was 0.3125 plus or minus. We wanted E to be 0. Actually, I messed that up. Our standard deviation is what it was before. Z is still 2.17, and what is our standard deviation? Now, our standard deviation changes. Sorry, I think I said it was the same. But it changes because our sample size increased. Remember, our standard deviation, part of that formula of sigma sub P hat, that is a big fraction divided by n. So if you remember what it was P hat times Q hat, so 0.3125 times 0.6875, and that was all over n. So if we make our denominator bigger. Oops, sorry. I didn't mean to put that mark there. So if we make our denominator bigger, it's going to make that entire fraction smaller. So our sample size is 405. Okay, so let's see what that equals. What our standard deviation equals. So it's 0.3125 times 0.6875 divided by 405, and then taking the square root of the answer. And so now our standard deviation is 0. Let's see, 0, 2, 3, 0, 0, 2, 3, 0, 3, 2, 1, 1. 321107. Okay, we don't actually need all those decimals. Let's round here, or round more here. 0.02303. That'll fit. Now, let's see what E equals here, because I told you that E should equal 5%, 0.05. Now let's see. Either I told a lie, or I can't do arithmetic. So let's see which. Let's make sure I'm right here. Okay, so we have. Let's see here. 2.17 times that answer. Oh, and it looks like I did all right. Looks like I did all right, because this is 0.499. 79. Oh, if I could type. Sorry. There's a 0 to start with. I was writing 50%, which is not what we wanted. 0.499079, but we can say that is 0.05. which is 5%. So we can limit our margin of error to 5% by increasing the sample size. Oh, I didn't mean to do that. Yes, by increasing the sample size to 405. Okay, so that was true for when we were estimating means, and now it's true when we're estimating proportions. Okay, that you can always increase the sample size and shrink your margin of error. Now, the only other way to shrink your margin of error is to decrease confidence, which we don't want to do. You know, we pick a degree of confidence, make that decision based on the level of confidence you want, and it's usually based 99% or 95%, and you don't want to decrease that level just willy-nilly. You want to once you pick it, you have good reason for it, stick with it. If your margin of error is too big, then you need to increase your sample size. Okay, that way we don't change the level of confidence, but we get a smaller margin of error. Okay, so we've talked about a lot of stuff here. Let's see. We answered our question up here. We figured out a confidence interval right here. Again, this was our answer. This 6.1% to 56.4%, that was our answer to our original problem, or if the solutions were requested in decimal form, this right here. Okay, but that was I think a good healthy discussion about sampling using a sample proportion to estimate a population proportion, and then the ways we could reduce the margin of error by increasing the sample size while not having to decrease our level of confidence. So hopefully that was a good discussion for you. Now you can use this example to work on some homework. Now I need to go call back my student who just called me, see what was needed there. If you guys have any questions, feel free to email me or stop by my office anytime at all. And I promise, unless I'm doing recording, I'll answer your phone call right away, or else I'll just have to call you back after I get done recording. All right, guys, have a good week. I'll see you soon.